Okay. Excellent. Well, I'm afraid we better leave it there. There is another question in the chat that you can, sorry, in the Q&A that you can have a look at. And we've moved through the urgent people. The next person on my list is you, Peter Ray. Are you still there?
Yep.
Vladimir,
yeah,
if you can. Excellent.
I'll share a screen if you'd like.
Excellent. So I think, Vladimir, have you stopped sharing your screen?
Yeah, could you unshare my screen, please?
Rick? Yep.
Thank you.
Excellent. Thanks very much.
Thank you.
Okay. Probably it's going to be try screen 2, and let's see.
So we're not seeing the slideshow. We're still just seeing your slides.
There we go.
Yep, excellent. And if you can put on, have you got video? If you'd like to put that on while you're speaking.
Video, as in?
So we can see you.
Okay, hang on. I'll just jump back out. Yeah, I must have double clicked.
Okay.
Let's see if that starts. We might just take a moment for it to restart. Is my picture up yet? Video?
No, still not seeing it.
Oh, there we go.
Ah, yes, excellent. We can see you now. Thanks very much, Peter.
And I'll just restart the presentation. Is that perfect?
Yes, we can see that. Thank you.
Right. Okay. G'day to everybody. Just like to share a bit about ISA mine lease, our exploration efforts here over a few years, and just going to talk about the Paroo fault and some other basement structures with some lessons from the core yard, and I guess an acknowledgement of all the fantastic work done by past MIM geos. So just a quick overview of the major structures of the Isa Valley. This is a 50-kilometre north-south map. Mount Isa fault is pretty prominent, pretty linear, and the Paroo fault adjacent to it. They're subparallel and on the gross regional side, and indicate pretty long-lived deep structure, at least underneath. The Mount Isa fault zone is what I call a band or a ribbon of deformation that is really quite a striking feature compared to the regional geology units on either side. There's also northwest faults that are quite prominent, and within the cover sequence 2 or Haslington group, these form south-dipping normal faults. And some of these were active during deposition of the Isa Basin, and you can tell that because of the difference in sediment thickness, the growth fault differences. And we have some areas of broken ground within this ECV package that I believe are beneath or reflect and indicate plumbing beneath the George Fisher and Hilton and Mount Isa deposits. So the Crystallina fault south of Mount Isa mine, and here I have in red the lead ore bodies and in yellow the copper ore bodies projected to surface. And green here is the Paroo fault, and I'll just turn the laser on, Paroo fault here with some folding, and we have the D1 or an early, what we think is an early northwest fault, Crystallina fault, which sort of cuts off the mine sequence at the south end of the golf course. And the deformation history you're all probably very familiar with, but hang on, next click. For some reason I'm not getting the next screen coming up. Okay. I'll just go down and try clicking the next button. There we go. The Lagoon Creek fault, which we say is a D1 structure, but the sort of puzzling thing, or the conjecture, is that when you get into the mine, you can walk along the path of this interpreted structure and see features through the town that you think might indicate its presence, and it goes through the nose of the Mount Isa Fault, the Urquhart Shear. So if they are interpreted to actually be the same fault, then there must be a fair bit of reactivation. Similarly, down here at the golf course, we have another fault axis, which is shown in the Paroo fault nose here. So, yeah, bit of conjecture. And the Mount Isa fault, well, Mount Isa fault, what age is it? D2, D4, D6. And then we also have the Leichhardt shear, which, once again, not easy to identify. It shows up well in drill core, but yeah, we think this is probably a D4 structure. So in cross section, we have the Mount Isa fault. We have the Paroo fault, which you can see the basalts or ECVs underneath, with the ramp at the north end of the mine. We have the Urquhart shear with the lead lodes on the west side mostly. And then in pale green, the 2% copper shell outline of the ore bodies. Most previous models of ore fluid migration have sort of suggested that the fluids probably came up the Paroo fault and then went out into the foliation or the west dip bedding. And common wisdom has always been that these mine faults in the hanging wall don't cut the Paroo basement. And I guess exploration for the last few decades has been focused on this sort of model where we've looked for either basement contact deposits such as the 3000 ore body, or for perch deposits in these hanging wall mine faults. And when we were looking for deposits that sat on the basement, typically we were looking for tears and dislocations that we thought had been propagated by northeast D3 deformation. And yeah, so here's a cross-section of the mine at the 36500. It's the underneath the mill. And you can see the variable thickness of the Paroo here, and all of the various coloured, both northwest and northeast and north striking mine faults interpreted. And more than that, actually measured in the mine where they impact on production. The Paroo fault, I have a photo on the right-hand side, which shows some of the rather chaotic fabrics we get in some parts of the Paroo, thicker sections, particularly underneath some of the ore bodies. And it's long-lived. It's a really old fault. It has multiple quartz carbonate vein stages, brecciation, boudinaging, and multiple reactivation. So I guess could have originally been a basin margin fault or a thrust, but it's pretty old. And if you look northwest in a 3D model at the entire ramp over about 8 kilometres of strike, in the north you can see that the Paroo itself is pretty steep, and whereas in the south part of the mine it's fairly flattish, undulating. We have a rollover at the 1900 ore body to the north, and east of the 1100 ore body and the 3500 ore bodies, it rolls over to near vertical on this east side. In 2016, Ben Andrews started a PhD with us, and he took we gave him a copy of our oxygen isotope database and a whole bunch of samples which he analysed and came up with this oxygen isotope flitch plan model. So we have from the left surface, 1,000 metres below surface and further. And I guess the simple takeaway from this was that he confirmed Waring's previous work that fluids seemed to flow from the south to the north, but really interestingly, it seemed to focus on a fault called Burnborough, this one here. In the northern part of the mine, the isotopes still indicated the Paroo was a major control on mineralisation, but didn't seem to be quite the case at the south part of the mine. So 4 years ago, we initiated a study of basement alteration, and I guess a major enabler of this was an update of our core yard catalogue, where we found a lot of lost core drill holes we hadn't seen for some time. And the major objective was to see if we could identify relevant hydrothermal signatures in the basement volcanics. Most folks consider the ECVs to be the source rocks for the copper ore bodies in the inlar. And I guess this study was also prompted by a drill hole in 2015, a kilometre north of George Fisher, where we found basalt with some quite convincing silica dolomite veins with chalcopyrite in them. So the 1992, there was a major revision of the interpreted mine geology, and Dave Morris, Steve DeCroix, Dale Sims. And one of the things, this is underneath my office at X41, and one of the things that stood out was this buck quartz thrust fault that they interpreted. And what they thought was the southern 1100 ore body here had been chopped off and could be hidden or blind down to the west. So in 1993, they embarked on a program, incredibly ambitious, where they drilled 25,000 metres of diamond drilling. And they didn't find a new ore body. And in 2017, Trevor Shaw here invited Dale Sims to come and re-look at our 3D models, and one of the things he observed was in the south part of the mine that when you look at the Paroo upper basement contact, that there was some ore that appeared to poke through that contact over 600 metres of strike. And at the end of a week here, looking at the data, he sort of made the comment that, he'd worked in the mine all those years, been involved in the interpretation, and sort of thought, well, in retrospect, why did they drill west looking for ore when potentially it was underneath the buck quartz fault? So we thought it'd be a great idea to pull drill holes out and do a relog, because the original basement holes, they only assayed where they could visually see copper, and they did it with the mine XRF bulk analyzer, and only for copper. So we thought we could apply some whole rock geochem. And the core, when it was pulled out, so here's two holes, or a master hole, D328, and a daughter hole, V1C. And I've portrayed in yellow the mine faults, the Burnborough fault here, the J46, which is a major bugger in the mine, the buck quartz fault, and of course the Paroo in green. And I have the Spears hanging wall fault or stratigraphic contact, which is the hanging wall to the Urquharts, and then I have the footwall native B in dark blue. And so we had the core laid out, and where it passed through the Paroo fault, we had vesicular basalt on the right-hand side of the photo, where 3 metres of foliated, folded graphitic schist. And the really interesting thing is that the foliation is actually vertical in that centre part of that core tray. There wasn't much evidence of any fluid flow. And so we thought, well, why was this pretty dry and dusty? Anyway, ploughed on, looking for the buck quartz thrust fault. And from our mine 3D model, we knew at what depth we should intersect, around about 12, 20 metres. And it just wasn't there in the core trays. The core trays had been stored in the car park and got flooded a few years before, so had been covered in mud. You can still see a few brown trails there. So as we were hosing this off, we were sort of surprised not to come across a major fault, because the buck quartz fault at the eastern end is 60 metres thick, and down here under the ore body is about 10 metres thick at least. And so to not have an expression of it in this hole was a little bit surprising, but we ploughed on, and down the bottom of the hole, we came across these quartz breccias. We had initially chlorite schist, or what I call vesicular chlorite schist. They are sheared up basalts. And then we ran into this brecciated basalt with stylolites. So
I'm looking at, sorry,
fault.
2 minutes, Peter.
Okay. And that there is the basement extension of the Bernborough fault. So essentially the butt quartz does not go through. It's the Bernborough that controls it. And we interpret this as a major flower structure with dilation on the east side, fluid flow coming up from underneath. And it sort of explains why the high grade was down here in the gully. It wasn't because it was a tear, it was because it was a throttle event point. And so that is the hydrothermal model for the south part of the mine, and it continues 700 metres south on 2 more drill holes. So that's what it looks like, the contact, chlorite schist, the silicified breccia, and there's the model in plan. It's all of the ore is east of the Bernborough fault, and it matches what Miller had sort of established in 2007. So just to skip through, this is the first, I think, mapped evidence of a deep plumbing system for the eyes, the copper ore body, particularly in the south part of the mine, where the fluids migrated out of basement, and mostly the Bernborough fault. Confirms the work of Miller with brittle dilation jogs as the major control. The Paroo is not the major conduit for the bulk of the copper mineralisation. The Southern 1100 has 60% of the ore, and it's likely there are other basement feeder faults like this under the mine, and Miller suggested as much as well. I think we should be targeting brittle second order fabrics with underlying northwest faults and within the Mount Isa fault deformation corridor. And the question is, how do we become advocates for the bleeding obvious and actually see what's in front of us? And here's Rick's favourite slide. You know, there's some really fascinating questions on the roles of models and psychology of creative thinking. I don't think we're as creative as we think. And for instance, none shall pass the upper basement contact is a classic case of group think in the mine here, and for us at exploration in the past. So observational geology is the only way to advance, plus some assays, thin sections, and some research. So just in case anybody has any doubts, I've got a fly through here of step through that in theory should, no, I'll have to try it again. Maybe it doesn't work. I'll try it again, try playing it. There we go. So, any questions?
Excellent. Thanks very much, Peter. Do we have any quick questions? Take one. I haven't got anything in the Q&A. Do we have anything from the panelists at the moment?
No.
No? Okay, so we are running a bit behind overall. Oh, sorry. Sorry, who am I hearing?
It's Peter, just stop sharing.
Okay, excellent. Thanks very much, Peter. And then
I've got a quick one
if
I'm allowed to.
Sure.
The 3,000, 3,500 sort of stand out as being off of there. Have you found a sort of the Bernborough version for them?
Yeah, actually, Miller had thought he'd found a couple of potential candidates, and yeah, there are some structures underneath, but I guess I haven't taken any deep drill holes from under those ore bodies yet and actually found major structures that I was happy with.
Thanks.
Excellent. No, thanks very much, Peter.